Hello, everybody, and welcome to the U.S. Operational Weather course. My name is Julian Castro. I will be your facilitator throughout this exciting journey. And I'm really hope you're having a fantastic day wherever you are. So let's get right into it with a brief introduction about this. Okay, we're going to separate this course into modules. So this is the first module. So this course has been prepared by Ansar in partnership with Aviation English Now. Couple of companies that have really joined forces and are committed to providing high quality aviation content. Now, who am I? Well, I'm an airline pilot, currently airplane instructor, A320 instructor, and simulator instructor as well on the same type of aircraft. I've been teaching weather for a couple of decades now. I started off teaching weather when I was a CFI in the United States, and then I've been also working on weather things on the airlines throughout many years now. So the main objective of this course is to provide you with enough understanding of basic weather concepts so you can apply this knowledge into real flying. I've felt many times on previous instances that I receive a knowledge that somehow I don't see the real application, or I don't connect that knowledge into my actual flying. So that is the main objective: understanding and application and correlation into your daily flying. Now, the courses are taking into consideration the fundamentals of weather, and then we are progressing into more intermediate stuff related to weather services and how to put that into application. So the contents, first of all, we're going to talk about the atmosphere basics. Of course, atmosphere is the most fundamental thing that we need to understand. Then we're going to talk about wind, all you need to know about wind, operationally speaking. Then we will be touching on stability and water state changes. Stability meaning basically learning to differentiate between a stable and unstable atmosphere and what are the challenges that this brings. Then we will be touching on clouds. Everything you need to know about clouds will be picked up here. Then we will dig into ceiling and visibility, air masses and fronts, which is a huge deal, especially when flying to the United States. We have fronts over there. Fronts really don't reach the Latin American or South American latitudes. So that is a big important thing we're going to talk about when flying into the United States, because this course has a US emphasis. And finally, we're going to talk about weather products and services. There is a enormous amount of tools that we can use effectively, from pre-flight briefings up to flying when we're on the aircraft. We can gather to take better decisions. So we'll be touching on observations such as METAR, radar pictures, satellite pictures. Also, we will be teaching forecasts like TAF, SIGMET, Center Weather Advisories, General Forecast for Aviation, Graphical Forecast for Aviation. And we'll also be including charts, of course, like surface analysis charts, winds, and significant weather charts, just to mention a few. This is a big part of the course. We're gonna touch on this on the latter parts of the course. I'm really excited about this part in particular. Now, all these course contents have been established in accordance with the pilot knowledge subject areas outlined in the FAA Advisory Circulars 006B and 0045H I highly encourage you to download these circulars. You can get them absolutely free from the FAA website. And actually, you can get the latest, most updated circular. The first one talks about weather. It's actually a weather book. And the second one, it's a weather services book. And you can also find these circulars printed by commercial providers at a cost, but you can absolutely have this on digital right now. So I highly encourage you to download this, okay? All right, important disclaimer, this presentation is for training purposes only, all right? It is not intended for use in actual operations. When you actually go there and fly, official publications and documents must be used, okay? So this is for training only. All right, so let's get started. All right, let's talk about the atmosphere. So the atmosphere is a mixture of gases that surrounds the Earth. Now, how high, how deep, or how wide is the atmosphere, depending on how you want to look at it, depends, okay? But we can say that it is fairly around 260,000 feet. Of course, there is not like a tangible limit between the atmosphere and space. You cannot say that, okay, 260,000, so this is the point where atmosphere goes, and beyond this point it is this space, because actually the atmosphere just fades into space. So there is not a definite limit, but it's around 260,000 feet. Now, the atmosphere is divided basically into 78% nitrogen, 21% oxygen, and 1% of other gases. This is the main composition of the atmosphere, and that percentage is maintained fairly constant throughout the atmosphere, especially in the troposphere, which is where basically all of, or most of, flying takes place. Now, the atmosphere is divided into layers. These layers share, the division occurs because each layer has different properties. So the first layer is the troposphere. As I just mentioned, it is where most of flying happens. And after the troposphere, we have the stratosphere. Then going further up, we have the mesosphere. And finally, we have the thermosphere. Now, some textbooks talk about the exosphere, others don't. But there's also another layer that is called the exosphere, that is basically where it fades into space, as I mentioned before. Okay, now between any two layers, we have a pause, which is like a boundary. Okay, so between the troposphere and the stratosphere, we have the tropopause. And between the stratosphere and the mesosphere, we have the stratopause. And then between the mesosphere and thermosphere, we have the mesopause. Now, all these pauses are important. For us, the most prominent and the most important one to keep in mind is the tropopause, because different things happen on the tropopause, as we will speak as we go on this course. There are other layers that are embedded within the layers that I just mentioned, and we will touch on those in the next slide. Okay, one of the most important things that happens on the different layers is the temperature behavior. The temperature changes differently depending on the atmospheric layer we are flying in. So the troposphere, the temperature behavior is basically a reduction in temperature as we increase altitude. It starts at about 50 degrees Celsius, if we're talking about a standard atmosphere, and it reduces at a rate of approximately 2 degrees Celsius per 1,000 feet until reaching the tropopause. Now, once we reach the tropopause, temperature will remain constant for a few thousand feet, and it will start increasing again on the stratosphere. It decreases on the mesosphere, and then it increases again on the thermosphere. Now, on the thermosphere, something interesting happens with temperature. The measurement of temperature is not the same, because under troposphere, for instance, the temperature is a measure of friction between the molecules. So you have higher pressure, higher friction, then that yields a higher temperature. Now that doesn't happen on thermosphere and then space. So the temperature in space is actually measured or is directly impacted by sun exposure. So if you have sun ray exposure, you have high temperatures. If you're in the dark side of the moon, for instance, or you have no sun ray exposure, then you have cold temperature. So it's a different measure of temperature. But going back to troposphere, it is definitely the friction of molecules, and it reduces as we go up until the tropopause. Tropopause, according to ISA, International Standard Atmosphere, is 36,000 feet. It is actually 36,089 feet. However, that is according to standard atmospheric conditions, a theoretical atmosphere. In real life, tropopause, the height of the tropopause actually depends on different things. For instance, on the latitude where we're at, it is highest on the equator, and it starts decreasing in height until reaching its lowest point on the poles. The season also affects the height of the tropopause, basically related to the temperature on that specific area. So higher temperatures, higher the tropopause, and once you start going down to colder temperatures, the tropopause starts going down. So you can actually see that sometimes that tropopause is around 54,000 feet on the equator, and then you can actually see on the charts how it starts going down towards the 24,000 value towards the poles. Okay. Now I mentioned that there are other layers embedded within the atmospheric layers. For instance, we have the ozone layer, and we've seen the ozone, and we've heard of ozone layer since we were at school, because it is a highly protective layer that we need to support us. So the ozone layer is basically high ozone concentration. And one very important thing to note here is that ozone is O3. And O3 comes from the breakdown of O2, and that chemical reaction produces heat. So the buildup of ozone, or the creation of ozone, produces an increase in heat. That is why on the stratosphere we see an increase in temperature with altitude. If you ask, why does the temperature suddenly starts increasing in the stratosphere? That is because the ozone layer. Okay, then ozone concentration starts going down, and temperature goes down as well on the mesosphere. Okay, and we have a second layer which is very important for aviation, which is the ionosphere. Ionosphere is, again, high ion concentration. And why is the ionosphere important for us? Because on that layer is where we have radio waves, especially high frequency, medium frequency waves, reflected back to Earth. And that is what makes HF communications so important for us. We can reach several miles in distance using HF radio, and that is thanks to the ionosphere. Ionosphere is more strong, or is stronger at night, and is weaker during the day, and that is why also we have to select the appropriate radio frequencies depending on time of day. Now, I mentioned International Standard Atmosphere, and this atmosphere is a common framework that was developed for us to work on the same basis. So it would be very difficult for a manufacturer, for instance, to provide performance data for the different atmospheres that we have out there according to different locations. That's very tough. So they said, okay, why don't we create a theoretical atmosphere with certain values that serve as a reference, and then you rather work from that reference and compare that reference to the real atmosphere, and that difference or that deviation will serve as a performance calculation. Okay, so International Standard Atmosphere, the values, you absolutely know these things already. We have temperature that is 15 degrees Celsius on ground, and it reduces at 1.98 degrees Celsius for every per every 1,000 feet. We can round up to 2 degrees Celsius per 1,000 feet. And that is true until reaching the tropopause, because in the tropopause, temperature stops decreasing. So if we, for instance, we think of 30,000 feet, so temperature reduces 2 degrees per every 1,000. So if we go up 30,000 feet, that's a reduction of 60 degrees. If we start at 15 degrees Celsius and reduce that by the amount of 60 degrees, then we can say that the standard atmosphere temperature at 30,000 feet is minus 45 degrees Celsius. And that's how we end up calculating delta ESA or ESA deviation values by comparing that standard temperature to real temperature. Okay, then we have pressure. Pressure, according to ISA, is 29.92 inches of mercury. We can also express that in millibars, which is 1013.25 millibars, or hectopascals, which is, for this matter, the same thing. And it reduces about roughly 1 inch of mercury every 1,000 feet. That is true. That is not a constant until the tropopause as temperature. The reduction in pressure is 1 inch of mercury every 1,000 feet, and that is true for the first 10,000 feet, around 10,000 feet, because the pressure reduction is not a constant. That a change in pressure starts reducing as we go up in the atmosphere. Okay, now how do we measure the pressure? Well, there are various methods for pressure measurements. We are going to talk about two of the most commonly known here, and the first one is the mercurial barometer. Mercurial barometer uses mercury, of course, and it works really simple. You take a pot and you fill it with mercury, and then you put inside of that pot filled with mercury a probe, and the pressure exerted by the atmosphere makes a quantity of mercury to go up inside the probe, and that height or that distance is measured, and that yields an atmospheric pressure value. So have you asked yourselves why pressure is given in inches of mercury? An inch is a distance pressure. It's a distance measurement, not a pressure measurement. So when we say 29.92 inches of mercury, what they're saying is the height of the mercury inside that tube is 29.92 inches. Now, the way we use to measure pressure in airplanes is by using an aneroid barometer. So the aneroid barometer uses a wafer, like a diaphragm, that expands or contracts depending on pressure. So the higher the pressure, more contraction on that cell, And as pressure decreases, that cell starts expanding, and that movement of contraction and expansion is then translated into a reading, and that reading is what we see, for instance, in an altimeter. That reading, that dial turning clockwise or counterclockwise, is basically the translation of an inner cell expanding or contracting. So that is how we measure the pressure in aviation. We also have other different scales like PSI, pound square inch. According to ISA, is 14.7 PSI. So you have a wide scope of options on how to measure the pressure.